welcome back. This is Unit 7.2 on the properties of solutions. In our last unit, last section, I should say, we talked about what a solution was, and now we're going to start talking about properties of solutions. This is page 624 through 628 in your textbook and 226 to 236 in your workbook. All right, so we're going to start off talking about the properties of solutions. We're going to talk about acids and bases in particular. And there's two types of acids and bases that we're going to be talking about. We're going to concentrate most of our time on Arrhenius acids and bases. Okay, Arrhenius acids and bases. All right, and acids and bases have different properties, and I've listed them out here, so go ahead and pause the video and then copy these down and you can restart. All right, acids have a tart or a sour taste, and this comes from several acids. It could be citric acid, malic acid, tartaric acid, or fumaric acid. And we know that sour candies like Warheads, Sour Patch Kids, Sour Punch straws are sour. Now, the Sour Patch Kids and the Sour Punch straws, if you look at them really closely, there's a coating on the outside. And this coating is crystals, and that contains, for the most part, fumaric acid, the last one that's listed there. That's what gives them their distinctive sour taste. And if you just pop it in your mouth and don't chew on it and let that outer coating melt off, then when you finally chew the Sour Patch Kid, that's where you get the really sweet part of it. All right, another property of acid is that when they react with metals, they produce hydrogen gas. So we saw that when we did our experiment where we were collecting the hydrogen gas mole rockets. We collected the hydrogen gas in the little pipette, and then we tested the sound of it. We mixed a zinc metal with hydrochloric acid and produced hydrogen gas with that. Another one is most foods are acidic. Most of the foods that we eat are acidic. And they do have other chemical properties that we'll talk about as we talk more about acids and bases. The properties of bases. Bases have a bitter taste. Probably the most common base that we know about that we use every day is soap. And if you've ever gotten soap in your mouth, then you know that it's very bitter. It has a very bitter taste. Bases are also slippery to the touch. So when you touch a base and then rub your fingers together, it's slippery. And again, they also have other chemical properties that we'll discuss as we go through this. So what's the definition of an Arrhenius acid and an Arrhenius base? And this was developed in 1887 by a Swedish scientist named Svante Arrhenius. And he said that a hydrogen-containing compound that dissociates to yield hydrogen ions in an aqueous solution is what an acid is. Okay, so let's look at this, a hydrogen-containing compound. So we have done formulas for acids, and we know that a common acid is hydrochloric acid. We've seen this before, and we've heard of this. So this is a hydrogen-containing compound that dissociates. Okay, so that word dissociates means to split apart. So this will split apart into hydrogen ions and chlorine ions. So we'll have hydrogen ions in water, and we'll have chlorine ions in water. It splits apart, it dissociates. Okay, and the definition of an Arrhenius base is a compound that dissociates to yield hydroxide ions. So a common base is sodium hydroxide. So this will dissociate, split apart to give us sodium ions and hydroxide ions in solution. Okay, so those are your two definitions. that we're going to be working with for an Arrhenius acid and base. All right, so some examples of acids and bases. We've already talked about hydrochloric acid, and this is a really common acid in chemistry. Out in the, quote, real world, hydrochloric acid, you can get it, they use it for all sorts of things. You can put it in your swimming pools to adjust the pH of your swimming pool. I know when I had a pool and we lived down at the coast of Texas, my swimming pool was always needing acid. Like once a week, I would have to put a cup of acid into my swimming pool to adjust the pH because it was getting to alkaline or basic. You get it at Lowe's or Home Depot, and you can use it for construction if you're redoing your driveway, putting either a coating on it or putting some more cement on it, and you don't want to, like maybe pea gravel or a layer of cement, and you don't want to rip it up and redo the whole thing, then what you can do is coat it with hydrochloric acid and it will melt parts of the cement. It'll actually melt it. You can wash it away with water, dilute it. You have to be very, very careful because it's very dangerous. And it'll leave your driveway pitted and rough so that the next layer of what you put on there to recoat it or resurface it will stick. It'll have something to stick to. Another common one is formic acid, and this is the acid that's in ants, that ants use, fire ants. When they grab a hold of your skin and they curl their abdomen around and they shoot formic acid out of their abdomen onto your skin. That's what the burning sensation is. They're actually getting an acid burn. They actually don't have a stinger where they sting you. They're shooting acid on your leg. Nitric acid, HNO3, this is used as an ingredient in rocket fuel, and it's also used to make fertilizer. Sulfuric acid, again, used to make fertilizer, and it's a component in batteries. Some of the old school batteries that we used in our cars, the big car batteries, had sulfuric acid in those batteries. Phosphoric acid is used in the production of semiconductors. Acetic acid is another word for vinegar, and we eat that all the time. And carbonic acid, this is the main component in limestone rocks. And when limestone is dissolved in the limestone that's in the ground, it's dissolved by carbonic acid. Then this will drip through the layers of the earth. And if it comes to an underground cave, then it will start forming, solidifying back on the top of the cave. And as it drips down, it will form a stalactite. And as it drips on the ground, it'll form a stalagmite. Okay. Blood, it's also, carbonic acid is also a component in your blood. It is an acid that regulates the carbon dioxide in your blood, and it also works to keep your blood pH levels, or the level of acid that's in your blood, at a normal, manageable level. All right, some common bases: sodium hydroxide, NaOH. This is drain cleaner. This is the main component in drain cleaners. And we don't really think about bases being as dangerous as acids, but they are. Now, the way drain cleaner works is most of the time what clogs your drains is organic material like hair and bits of food and grease. And what sodium hydroxide does is actually melt that, make it more liquefied so that it is easier to be forced through the drain. So drain cleaner, sodium hydroxide it will damage your skin and cause massive burns. Potassium hydroxide, KOH, it's a component in liquid soap. Calcium hydroxide is a pickling agent. It's what we use to make pickles out of cucumbers. And magnesium hydroxide is the common name is called milk of magnesia. And this is a over-the-counter medication that you can get to help with reflux or acidic stomach. Like if you were to eat, like spicy foods or maybe sometimes pizza that's real greasy, you'll get an upset stomach, and you can use milk of magnesia instead of Tums. It doesn't taste very good. So it's not very popular because a lot more over-the-counter drugs that taste better have been developed for that. But that's still out there. It has got a distinctive blue bottle like this. It's also a mild laxative, and it's called milk of magnesia, and it's magnesium hydroxide, magnesium. So that's where they get the name. All right, so when we're going to talk about electrolytes. So if you look down here at the bottom, electrolyte, when these acids or really any salt dissolves or doesn't dissolve in a liquid, the degree to which it dissolves is called an electrolyte. So let's look at three different cases: a non-electrolyte, a weak electrolyte, and a strong electrolyte. So a non-electrolyte is when you have in a solution, either it doesn't dissolve at all, if it's a salt, or it does dissolve, what we call dissolving, but it doesn't dissociate, it doesn't split apart, it just dissolves. So we have this terms that we use that really aren't describing what's happening in the liquid. Like we say dissolve. To us, dissolve means that it goes away, right? When you put it in liquid, it'll go away. But dissociate, when we use that term dissociate, when we put this down into a liquid, dissociate means that it splits apart. The actual chemicals that make up that compound will split apart. Like in an acid, we talked about this word dissociate here. So we are going to talk about the difference between dissolving and dissociating. So dissolving, let's talk about sugar. Sugar is a big molecule, C12H22O11, and you see that right here. So this big clump of different elements that are stuck together, that's the separate sugar molecules. Now, when we say that sugar does dissolve, what we mean is these molecules are clumped together to form a crystal. Okay? And what happens is these molecules, when we say it dissolves, we put it down in water, these molecules break apart from each other. But the components of that molecule, the C12, the H22, and the O11, they stay together as a molecule. They don't separate. So yes, this does dissolve, but it doesn't dissociate. It doesn't split apart. And when something does not dissociate like this, we call this a non-electrolyte. And an electrolyte, we can tell if something is an electrolyte because it conducts electricity. So we have this mechanism here set up where we have this beaker, that in this beaker we have pure 100% deionized water. So all it contains is water molecules, nothing else is in there. And then we place sugar in there and dissolve it, and then we test it. We run an electrical current through here. And if this was an electrolyte, if it had these different ions, these components of this splitting apart, it would conduct electricity. We can see here that the light bulb is not on, so it doesn't conduct electricity. And if we were still in school, I could do this demonstration for you. I have one of these mechanisms, and I could show you that I could dissolve sugar into water, and then it is not going to conduct electricity. Okay, you may be skeptical and say, well, these cords here or off screen. They're not in the picture frame. So how do I know that they're really running electricity through it? Well, you don't. You're just going to have to take my word for it. But I could show you, if we were still in school, that this does happen. So let's compare that to a weak electrolyte. So here we have HC2H3O2. And if we look back, we'll see that that is acetic acid. This is vinegar. So when we pour vinegar into water, it does dissociate. It does dissolve. So here, these molecules with the red and the two white, that's your water molecules, okay? And so here, this clump here, this is the acetic acid. This is the one hydrogen, two carbons. So the black is the hydrogen. Two carbons. And then here we have, or the white could be oxygen. Yeah, because there's two of them. So we have two oxygens. The red are the two carbons. And then the white ones are going to be the hydrogen, because we have a total of 4 hydrogens. So 1, 2, 3. And then this one is 4. So here it's together. Here's another one that stayed together. Here's another one that stayed together. Here's another one that stayed together. But look at this one. This particular one, the hydrogen split apart. Okay. So there are electrolytes in this liquid. And we can see here that the light bulb is on, but it's not on very brightly. It's very dim or weak. That's because vinegar is only slightly dissociates when you put it into water. So you may have several molecules that don't split apart, but then you are occasionally going to have one where the hydrogen does split apart from it. Okay, now let's compare a weak electrolyte to a strong electrolyte. So here we have sodium chloride, and this is table salt. And here's the water. Okay, the table salt, here's the sodium part, the positive ion. Here's the chlorine, the green. And if we can look at this, we can notice that none of these purple and green molecules are still together. So every single molecule of salt that was placed in this solution has dissociated and split apart. And that's the difference between a weak electrolyte and a strong electrolyte. Now, again, in a weak electrolyte, most of them stay together. Occasionally, you'll have one that splits apart. And in a strong electrolyte, every single one of them will dissociate. And we can see here the light bulb is very bright. So that's a strong electrolyte. So that's what's happening on a molecular level. Okay, where's my cursor? There it is. All right, so let's put that in a chart form. So go ahead and pause and write down this chart. Okay, so a strong electrolyte is made with a strong acid or a base, a soluble salt, so a salt that dissolves in water is soluble in water. And when I say dissolve, I mean dissociates, splits apart. And some examples, H2SO4 is a strong acid, NaOH is a strong base, and then sodium chloride is a soluble salt. Okay, and so we said that the ions that make up that compound dissociate. So we're going to try to get away from that word dissolve. Dissociate 100% in a solution. Dissociate means split apart. All right, and so over here in this example, for a weak electrolyte, it's made from a weak acid or weak base, an insoluble salt. So that's a salt that on our solubility chart is insoluble. So a weak acid would be like vinegar. Okay. A weak base would be, an example would be magnesium hydroxide. And an insoluble salt is any of those salts on the solubility chart that are insoluble. So silver chloride, for example, would be insoluble. Okay, and these are ions that make up the compound, dissociate less than 100%. So here, strong electrolyte, 100%. A weak electrolyte is anything less than 100. It could be 99%, and then it's considered a weak electrolyte. A non-electrolyte is any polar covalent compound, like sugar is a polar covalent compound. Any of those, the atoms that make up the compound or molecule do not dissociate at all, 0%. So here we have 100% is a strong, 0% is a non-electrolyte, and anything from 1% to 99% is considered a weak electrolyte. Okay, and so we need to have a list of strong acids and strong bases. So these are all of the acids that dissociate 100%, and these are all the bases that dissociate 100%. Now this list is in your reference materials. So let me just bring that up real quick and show you where that is. On our reference materials, okay, right here. These reference materials, here are your list of strong acids and strong bases. So you have that list right here on your reference materials that you can refer to as we go through and look at this section on acids and bases now. Okay, so make sure you have these in your notes, or you have that reference material there available for you. Okay, so the way that we measure the strength of an acid or a base is what we call pH. And this is a term that was developed during the study of acids and bases. And I have read and been told that pH stands for the power of the hydrogen ion. And so pH is a measurement of the concentration, there's that word concentration from our last section on solutions, of hydrogen ions in a solution. So it's a measurement of the amount of hydrogen ions that are in a solution, and that's what we call pH. And here is a common chart here for different pH values. pH runs from a 0 to a 14 is the pH scale. And so you'll see like shampoos, they say are pH balanced or pH neutral. And neutral on the pH scale is, what's the number between 0 and 14? 7. So 7 is going to be completely neutral on the pH scale. And then as you migrate either to the left or to the right of that 0, think about it as a number line. As you migrate from the 0 outward, from the 7 outward, then you're getting stronger and stronger. So if 7 is neutral, then 6, which is right next to 7, is only going to be slightly acidic. And 8, which is above 7, is only going to be slightly alkaline. So the most acidic compound, hydrochloric acid, is going to be way down here at the end of the scale. And then on this one, the most acidic base is going to be way up here at the 14 end of the scale. And then you can see we have other things. Okay, so most of our foods are acids. So mineral water, wine is about a pH 4, Coke, pH 3. Tomatoes are also a very popular food that we eat that are acidic. That's, I think, somewhere around, I don't want to guess, but it's acidic, I know for sure. I have a list on one of your worksheets that you're going to get that lists a whole bunch of foods and their pH values. And there might be a list also in your reading that you're going to be doing in your book over acids and bases. There might be a page in there that lists the different pH values of food. There is. It's on page 634 of your book. There's a pH scale there, and it has lemons and tomato juice and coffee and milk, things like that. Okay, so pH, the main takeaway of this part is that pH is how we measure the level of acid and base, and it's just a measurement of the concentration of the hydrogen ion that's in the solution. How much hydrogen ions are in the solution. Okay, and old school, or it does still have different applications today. There are what we call indicators that we can use in a liquid to find the pH of the liquid. Or if we're trying to test the liquid for different properties, then these different indicators can be used. So say, for example, phenolphthalein right here towards the bottom. This is a real popular one in chemistry that we use when we are trying to neutralize or what's called titrate an acid, where we have an acid and we're going to add a basic solution to it to bring the pH up to a 7. And when it approaches a 7, up to this point in any of the acid range, phenolphthalein is going to be clear. But once you get it up to 7 and just above 7, like to 8, then you start getting a pink color in the phenolphthalein, and that's when you know you've neutralized this acid because it starts turning pink. So that's why we call it an indicator, because it changes colors to indicate a change in the pH. And we have all of these different indicators that turn different colors at different pH levels. So if you wanted to, say, for example, know when something is around pH 2, then you would use thymol blue, because it's going to be, well, up here it's also pH between 8 and pH 9. It has green and yellow and blue colors. But if you had something that was in this range and you wanted to bring it down to this pH, then you would see a color start to appearing around this pH range. Okay, but more commonly in our modern technological times, we use probes, so pH meters. And here's an example of just one type of pH meter. It has a device here that registers the pH, okay, a little meter. And then you have a cord that actually has a probe on it that you can put in different materials. Though this picture shows one in the soil because he's measuring the pH of the soil. But you can measure pH of any liquids, like you could put this into milk and it would register a pH for you on the meter. And there are some that don't have a needle like this and a scale. It's actually digital. So it has a digital readout so that when you're taking the pH using a pH probe, it will tell you to 2 or 3 decimal places what the pH is. All right, so we have been talking about the definition of a pH as the amount of hydrogen ions that are in a solution. And so you're going to see hydrogen ion, this term hydrogen ion thrown around, and you'll also see the word proton thrown around or talked about. So I wanted to make sure that I pointed out the difference between a hydrogen ion and a proton. So let's look at a hydrogen atom. So here's a model of a hydrogen atom. This is called a Bohr model. We talked about these when we were talking about atoms. So for a hydrogen atom, we have our nucleus here that's in the center. We have one proton, and we have one electron in a hydrogen atom that is around the nucleus. To make an ion, okay, so by definition, let's recall what an ion is. An ion is an element that has gained or lost electrons. So if we take this and we remove this electron, so I'm actually going to remove this electron, then we see all we have left over here is the nucleus that has a proton. So this is called a hydrogen ion, okay, because we've removed that electron. Now, this is also called a proton because in hydrogen, when you remove the one electron, all you have left over is the proton that's in the nucleus. So this is a proton and it's a hydrogen ion. So there is no difference between a hydrogen ion and a proton. So when you see these terms used, they're interchangeable. They mean the same thing. Sometimes you're going to see in your reading hydrogen ion. Sometimes in your reading or in problems, you're going to see proton. So it's the same thing. No difference whatsoever. Okay, so let me get there you go. The electron's back. This is your hydrogen atom. Okay. All right, so now the mathematical. Scientists, as I told you, measure the strength of an acid by the pH. And so there is a mathematical formula for actually calculating pH. And once you see here in this diagram, once we have the pH, we can calculate how much hydrogen ion is in there, how much hydroxide ion, and then we can calculate something called pOH. And when you have any one of these pieces of this square here, you can calculate all the others. So in your reference materials, the only formula that's given to you is the formula for pH right here. And we can either derive these other ones or we can memorize them. It doesn't matter. All right, so let's start at the top. Kw is the dissociation constant for water. And when we see these brackets, that's another way to talk about concentration. So in 7.1, we were talking about molarity. Molarity is the unit for concentration. So when we're talking about a 1.1 molar solution, we use this capital M. So another way to describe molarity is by using the brackets. So we could get rid of this unit and then put brackets around this, like square brackets like this, and it means the same thing. Okay, so it's read as the same way. It's just a different way to write it. So this is 1.1 molarity. So the dissociation constant for water is we take the concentration of our hydrogen ion that's in a solution, multiply it by the concentration of the hydroxide ion in the solution, and that's always going to give you 1 times 10 to the negative 14. Okay. So this is what's called the dissociation constant for water. Because water, H2O, we know sometimes we write it as HOH, and water auto-ionizes, which means that when you have water, these split apart, okay, into hydrogen ions and hydroxide ions, and then they come back together. So it goes back and forth between this and this. Okay, and the amount of, at any one time, the amount of hydrogen ion multiplied by the amount of hydroxide ion that's in a solution will always give you 1 times 10 to the negative 14th. Okay, the formula for calculating pH is the negative log of your hydrogen ion concentration. So here's a new button on your calculator that we're going to start using, and it's the log button. So if you want to grab your calculator and find that, it's usually on, like if you have your numbers 0 through 9 plus your negative sign right here in the center, your log buttons is going to be just to the left of that somewhere. pOH is the negative log of the hydroxide ion concentration. Okay, so OH, hydroxide, pH, hydrogen. And when we have pH and pOH, when we add those two values together, we're going to get the number 14. Okay, and so look, we see that number right here. Okay, so log is a mathematical function that we're going to use, and we're going to be using log that's in base 10, the base 10 log. And you may be hearing about this if if you're taking like Algebra 2 this year, then, or maybe Algebra 1, I'm not sure, your math teacher is going to be talking about logarithms. All right, so the pH and the pOH value added together is going to give you the number 14. And if we have the pH, then we can calculate the concentration of the hydrogen ion, and that's 10 to the negative power of the pH. And same thing with the concentration of the OH. It's 10 to the negative pOH. Okay, so let's look at our calculator. Here we see the TI Inspire calculator. And I want to point out right over here, this button right here, it says log right above this key. So when we're going to, and it could be a second function on your calculator as well. So if you downloaded the TI Inspire calculator software that you see here, the one that I sent y'all in the announcements, then this is what you have right here. And this is the calculator, but it's just the software for the calculator for the computer. And so when we're going to calculate the log, the negative log of the hydrogen ion concentration, we're going to use the control key, and then we're going to hit this button here to get the log. So we would do the negative, okay? And then we would use this key, negative log. Now you're going to see this come up on your screen because the logarithms are in different bases. Like we have a base 12 log, a base 14 log. But for this, we're going to use common log, which is base 10. So we have to go ahead and put in a 10 there to show that it's base 10. And then here is where you're going to put in the hydrogen ion concentration. Like we may have a concentration of 1 times 10 to the, that's the EE button, times 10 to the negative 7. Oops, that's 0.7. Okay, let me do it over here, to the negative 7. So if we take the negative log base 10 of 1 times 10 to the negative 7, we're going to get a pH of 7. Okay, so this is the pH when this is the concentration of hydrogen ions. All right, so that's how you use that. And we'll come back to that in just a moment. All right, so make sure that you pause the video and you have all of these written down. And since we're working at home, then you can go ahead and use this as you're taking your quizzes. Now I'm recording this video during the coronavirus outbreak, so that's why I'm talking about. If you're seeing this after that, then that's what I'm talking about taking your quizzes at home and being able to use this. When we're in school and in session, you have to memorize these, and you can't have these out during a test or a quiz. The only one that's given to you is this one on your reference materials. All right. So just to show you how you use all these in a calculation, here we're given the hydrogen ion concentration as 1 times 10 to the negative 4th. And I'm going to show you how you can calculate all these others and to tell if this is an acid, a base, or if it's neutral, because we're going to be doing, these are the calculations that we're going to be doing. All right. So to get the pH, remember the formula for pH is the negative log of the hydrogen ion concentration. Okay, and so the hydrogen ion concentration is given to us right here. So we're going to substitute this number into this spot right here because see, it's the concentration of, or the brackets, hydrogen. Here's brackets, hydrogen. So this is the negative log of 1 times 10 to the negative 4th. So if we go to our calculator, we do the negative log, and this is base 10. Move our cursor over. You hit this button right here to move your cursor over. 1 times 10 to the, so that's the E button, -4, enter, and the pH is 4. Okay, so we go back and we say the pH here is 4. Now we can answer this question here, because to decide if something is an acid, a base, or if it's neutral, we look at the pH. Okay, not the other values, but the pH. So this is pH 4. So let's go back to this pH range right here. So it's pH 4 here. So remember, here is the dividing line, 7. Anything below a 7, and this is a 4, is going to be in the acid range. Anything above 7 is going to be in the base range. Now, neutral is when it's straight up 7, not 6.9, not 7.1, 7.0. Straight up 7.0 is going to be neutral. Okay, so this is pH 4. Oops, wrong screen. This is pH 4, so this is an acid. Okay, so what is the hydrogen ion concentration? Okay, so the hydrogen ion concentration, where is it? Right here. So it's 10 to the negative POH. So we need the POH to calculate that. So let's look up here. Can we get POH from any of these up here? Well, if you look at this one right here, pH plus POH is equal to 14. So pH plus POH is equal to 14. Well, if I have the pH equal to 4, 4 plus some number is equal to 14. Okay, so algebraically, we can figure this out, and this is such a simple algebra problem that we can do this in our head. We now know that the POH is a 10. 4 plus 10 is equal to 14. So our POH is 10. Okay, so now we can calculate the concentration of the hydroxide ion, because that's 10 to the negative POH. And we just calculated what the POH is. So this is 10 to the negative 10. Okay, and so when we use our calculator for that, and I hope this calculator is set up, this button right here, 10 to the X, if we push that, we're going to get 10 to this. And if we put in a negative 10 here and hit enter, then, oops, it gives us a fraction. So we can hit control, enter, and it's going to change it over to a decimal. Okay, so this is 1 times 10 to the negative 10. So that E, 1 times 10 to the negative 10. So our concentration of our hydroxide ion is 1 times 10 to the negative 10. Okay, now look at this. Hydroxide ion times the hydrogen ion is going to give us 1 times 10 to the negative 14. So when you multiply these two together, you're going to get 1 times 10 to the negative 14. So the properties, when you're multiplying exponents, numbers that have exponents, you're adding those together. Okay. And that's just another one that you should know that's not on your list there. All right, so another problem. Here we're given our our hydrogen ion concentration is 1 times 10 to the negative 11th. Okay, so again, the pH is the negative log of your hydrogen ion concentration. So this is the negative log of 1 times 10 to the negative 11. Okay, so let's go to our calculator. Okay, so this is the negative log, and it's base 10. Hit this button right here to get over here to this box. And it's 1 times 10 to the negative 11. Enter. And it's 1.1 times 10 to the first power. All right, so on our calculator, we get 1.1 times 10 to the first power. But pHs are never expressed as this. Remember, pH is anything on the scale of 0 to 14. So we have to convert this from scientific notation to regular notation. Okay, what does this mean? This 10 to the first power means we move our decimal over one spot. When we do that, it's going to give us 11. Okay, so the pH here is 11. So is this acid, base, or neutral? Well, remember 7 is neutral. Anything between 7 and 14 is a base. All right, if our pH is 11, we can calculate our pOH because 11 plus some number is equal to 14. So our pOH is going to be 3. And if we have our pOH, we can get our hydrogen ion concentration because this is 10 to the negative pOH. So when we put this in our calculator, 10 to the negative 3, that's going to give us 1 times 10 to the negative 3. Okay, so this is going to be 1, let's do this, 10 to the negative third power. That's going to be 1 times 10 to the negative 3. Okay, so you may see a pattern that when you have 1 times 10 to the negative 4, the pH is going to be 4. It's going to be this exponent as a positive number. And when we have the pOH as 10, we're going to see that the concentration is 1 times 10 to the negative of that number. Okay. Now, however, all of these coefficients here in this scientific notation aren't always 1. But this works if it's 1. Okay. So on this next example, oh, there is not another example. You're going to see in your problems that you're going to do that those numbers are not always 1. Sometimes they are, but most of the time they're not. All right, so let's look at some concept problems. Pardon me. As the pH increases, the pOH, and this is either looking for increases or decreases. So let's look at this. So as our pH increases, oops, wrong way. As our pH increases, so here we had a pH of 4 and our pOH was 10. Here we had a pH of, where is it? 11, and our pOH was 3. So as our pH increases, the pOH decreases. Because think about this. pH plus pOH is equal to 14. So as our pH increases, this is going to decrease. If this is 9, this is going to be 5. If this is 10, this is going to be 4. If this is 11, this is going to be 3. So as this pH increases, pOH decreases. Okay. As the pH increases, the hydrogen ion does what? As the pH increases, so as the pH goes from 1 to 7, okay, so the hydrogen ion concentration at 1 is 1 times 10 to the negative 1, and at 7 it's 1 times 10 to the negative 7. So as the pH increases, the hydrogen ion decreases. Because the strongest acid is going to be 1 times 10 to the negative 1. Okay. And that has, as you go up, it's going to be 1 times 10 to the negative 7. As you go up in the pH scale, there's less and less of these hydrogen ion concentrations. Because a real strong acid has a lot of these, a big concentration of hydrogen ions. A weak acid has very few. Okay, and as the pH increases, the OH also increases. So as we're going up from 1 to 7, this is getting lower, but this is getting higher. Remember, the hydrogen ion concentration and the hydroxide ion concentration are in a balance with each other. So as this one goes up, this one goes down. As this one goes down, this one goes up, because it's a balance between these two in a solution at any one time. Okay, and as the pOH increases, okay, so this is the another statement, as the pOH increases. So let's think about this. As this one increases, the hydrogen ion, we're going to skip this blank right here. So as this one increases, this one is going to decrease, because remember, I just said they're in a balance with each other. Okay. And as the pOH increases, so as this goes up, okay, the concentration of the hydrogen ion, it's talking about pOH and the concentration of hydrogen ion here. So as the pOH increases, so let's look at that, pH plus pOH. Okay, so as this increases, the concentration of the hydrogen ion, as this number goes up to 14 from 7, so the pOH is increasing from 7 to 14. As this goes up, increasing. Okay, and let's talk about this, because this is going from 7 to 14. So at 7, we have very little concentration of OH ions, because it's almost neutral. It's almost no concentration. And so as we go to 10, the hydroxide ion is getting more and more. And then finally, as we go to 14, that means the concentration of hydroxide ions is a lot. So as this number increases, it's kind of the opposite of this one. As this number increases, the hydroxide ion also increases. Okay, and as the pOH increases, the pH decreases. Because remember, you add those two together and you get 14. So as this number is getting bigger, this number has to get smaller, because pH plus pOH is equal to 14. So you kind of have to stop and think about these. Really understand what's going on in that 1 to 7 scale. You may have to watch this section a couple of times and then stop it and really take a moment to process that in your head. Okay. But once you do, then it's easier to, think about these and get this information straight. And it will come with time. Okay. It will come with time. All right. So I'll pause the video here and write this down. Okay, in an acidic solution, so we're thinking about a solution that is pH 1 to 7. Okay. In an acidic solution, the concentration of hydrogen ions is less than, stays the same, or increases. Okay. Well, since pH, or acid and base, is measured by the hydrogen ion concentration, the more hydrogen ions you have, the stronger the acid. Now remember, since this goes from 7 away, and this is a base, and away from 7 this way is an acid, okay? The stronger the acid, the lower the number, the more hydrogen ion concentration you have. Okay, so in acidic solution, the hydrogen ion concentration is less than, the same, or increases. Increases. Okay, so acidic solutions, the hydrogen ion concentration increases. And pH is low, while the pOH is high. Okay, the hydrogen ion concentration is high, while the OH concentration is low. So these are in a balance with each other. They're always opposites. All right, so I'll move the screen down so we could see the bottom part here. We're going to be talking about an alkaline solution. Alkaline is another word that means base. Okay, so when you see alkaline, it means base. All right, so we have here the hydrogen ion concentration is less than, stays the same, or increases. Well, let's think about that. So for an acid, we just talked about hydrogen ion concentration that's high. And hydrogen ion concentration is always in an equilibrium with hydroxide ion concentrations. So these two are in an equilibrium. So if hydrogen ion concentration goes up, then that means this one goes down. And if this one goes up, that means that this one is going down. They're the opposites. So in a basic solution, the hydrogen ion concentration is always going to be less. It's going to go down because in a basic solution, hydroxide ions are what's increasing. Okay. In an acidic solution, it's the hydrogen ions that are increasing. So hydrogen ion is less than in a basic solution because hydroxide is more. Okay, so let's talk about pH and pOH. So in a basic solution, the pH is going to be high. Okay, so remember, it's 1 to 14. Okay, and then in an acidic solution, it's 1 to 7. Okay, and 7 to 14 is a basic solution. So anything that's basic is going to be 7 to 14, which is going to be considered the high end. And if pH is high, the pOH is going to be low. So if we have pH of 13, okay, so that's very, very basic. That's a really strong base. If we have a pH of 13, since 1 plus 13, okay, is equal to 14, if our pH is 13, our pOH has to be 1 because both of these have to equal 14. So that's going to mean your pOH is low. Okay. And in an alkaline solution, the hydroxide ion concentration is high. We just talked about that right here. Okay. And if this is high, That means that this is going to be low. Okay, so always think about the pH scale, okay, and then 1 to 14, this pH is where we get the numbers on the pH scale. It comes from the hydrogen ion concentration. So pH plus pOH is equal to 14. So when you add those together, and these are in a balance. If this is high, this is low, this is low, this is high, etc. Okay, so you have to, on these kind of concept questions, at least for me, now this may come much quicker for you, but for me, I have to stop and actually talk myself through this and visualize it. But you'll get there. All right, so you're going to see a chart like this on the worksheet that you're going to get, that you are going to be working out. And this is just exactly like this right here. So you're going to be given one piece of the information, and then you're going to have to figure out the others. All right, so here we're given the hydrogen ion concentration is 1 times 10 to the negative 8. Okay, and so if we know that, we can get the pH. Now remember what I said, if this is 1.0 here, then the pH is this exponent as a positive number. So the pH here is going to be 8. And if the pH is 8, 8 plus pOH is going to be equal to 14. So this is going to be 6, because 6 plus 8 is 14. Okay, and if this is pOH is 6, we can get this is 1.0 times 10 to the negative 6th molar. Okay, now we can decide if this is an acid, base, or neutral. Well, it's pH of 8, so it's going to be basic because it's higher than 7. All right, so we have a pH of 5 here. We can automatically do this one. So this is going to be acid because it's lower than 7. And if pH is 5, pOH is 9. Okay, keep the same number of sig figs, 9.0. If this is 5, then the hydrogen ion concentration is 1.0 times 10 to the negative 5th. And if this is 9, it's going to be 1.0 times 10 to the negative 9. Okay. Now, 12.3. This is where we start getting into numbers that are not 1.0. When you have decimals like this for pH and pOH. So let's see how we do that. So if the pOH is 12.3, 12.3 and this have to add to 14. So how can we calculate this? Well, take 14 minus 12.3. Okay, so let me grab the calculator. So 14 minus 12.3, that gives us 14 minus 12.3 is 1.7, okay? It confused me a little bit because it's times 10 to the 0. Remember, times 10 to the 0, you don't move your decimal any. So it's 1.7. Okay, so we have a pH of 1.7. Is this acid, base, or neutral? Well, this is way below 7, so this is a very strong acid. Okay, so remember, the farther you get away from 7, the strength is increasing. Okay, so now we need to calculate the concentration of hydrogen and hydroxide. So we have the pH and the pOH. So remember, to get the hydrogen ion concentration, it's 10 to the negative pH. So it's 10 to the negative 1.7. And you don't have to write this. You would write this on a separate sheet of paper. I'm just writing it here because I don't have room to write it anywhere else. So you're going to have a separate sheet of paper that you work this out on. So 10 to the negative 1.7. So I'm going to push this button, get 10 to the power of negative 1.7. Okay, so here we go. This is now a decimal. And we're going to do 2 decimal places. Actually, let's do, well, this is going to be really close. So let's just say 2 decimal places. So 1.99 is 2 decimal places, but we have a 5 here. This 5 is going to bump this 9 up, which is going to bump this 9 up, which is going to bump this number up. So it's 2.00 times 10 to the negative 2. Let's go back. So 2.00 times 10 to the negative 2 molarity. Okay? And this is going to be 10 to the negative 12.3 for this one. So 10 to the negative 12.3. Okay, 2 decimal places, 5.01 times 10 to the negative 13. Okay, 5.01 times 10 to the negative 13. Okay, because these exponents can't be decimals. Because you can't move, think about that. You can't move that, because this tells you how many times to move the decimal, right? So we're going to move the decimal 2 times to the left because it's negative, anti, so it's left. So we can't move the decimal 2.5 times. You can only move this decimal whole numbers of times. So these have to be whole numbers. Okay, so that's why you're getting, when you have a decimal as your pH and POH, that's why you're getting these numbers now that are not 1.0. Okay, easy peasy. All right, so for our last example, we have 6.4 times 10 to the negative 3. So we need to calculate pH. Okay, so this column is POH and pH. All right, so remember, negative log of the hydroxide ion concentration gives us POH. Okay, so to get this, it's going to be the negative log of the hydroxide ion concentration. So we're given the hydroxide ion concentration here, so it's the negative log of this. Okay, so that's 6.4 times 10 to the negative 3. Okay, so 6.4 times 10 to the negative 3. Okay, so it's base 10 log, remember that. 6.4 times 10 to the negative 3. The POH is 2.19. Okay, so we're going to have 2.19 here. So to get this one, it's 14 minus 2.19. So 14 minus 2.19. That's going to be 1.18. 1.18. And to get the concentration, it's 10 to the negative 1.18. Okay, so 10 to the negative 1.18. That's going to give us 6.61 times 10 to the negative 2. Molarity. Okay, so the pH is 1.18. That's really, really acidic. Okay. All right, so that's it for 7.2. Make sure that you work out those problems that are on the worksheet and then take your quiz. All right, so make sure you also slap that like button right across the face. It's really important that you click on notifications so that you can be notified of when I put up videos on YouTube, so that you can see examples if someone requests examples of this being worked out. All right, have a good day.